Hello. Now we are going to start our second tutorial. The second tutorial is about integral calculus with vectors, and integral calculus is not as straightforward as the differential calculus with vectors. So, we need far more attention in this tutorial and also solving subsequent problems after working out this tutorial. Let us see what kind of problems we handle in the integral calculus with vectors. So, we know the Stokes theorem. Stokes theorem tells us that the curl of a vector quantity, if we perform a surface integral of that, that is equal to the vector quantity without taking a curl integrated over a closed line that encloses the surface. That is Stokes theorem, and we have been given a vector field V equals x y x cap plus 2 y z y cap plus 3 z x z cap, and we have been given a shaded region in this picture. We have x y z Cartesian coordinate system, right handed Cartesian coordinate system, and in this we have a triangular region on yz plane, and we are supposed to verify Stokes theorem on this surface. So, on this surface as well as the lines that we have drawn using arrow. So, the line elements will go along that arrow. So, what would be the direction of this surface? If we consider these line elements, then a cross product will tell us that the surface direction will be out of the screen. So, assuming the direction of this area element out of the screen and the direction of the line elements are as shown by the arrows, we will try to verify Stokes theorem. So, you can pause the video now and try verify it yourself and then restart the video. So, what is Stokes theorem? Stokes theorem is the surface integral of curl of V dot dA that is equal to closed line integral over V dot dl. We are supposed to verify this theorem, and how do we verify this? We first calculate the curl of this vector field, and for the given vector field the curl will be minus 2y x cap minus 3z y cap minus x z cap. And now we can see that we can consider an area element like the one shown here in the picture. So, the area element is shown by these two parallel lines here. It is a parallelogram that we have. No, it is not a parallelogram, it is a trapezoid that we have here, and if we move this trapezoid along z axis, we can cover the entire area of this triangle. The line, the slanted line that we have here connecting z and y axis, the equation of that line is y equals 2 minus z. With that, the expression for this area element we can write down as dy dz x cap. X cap is outside the screen, above the screen, and curl of the vector dot dA. So, dA is along x cap, only x component of the curl will matter here. So, the curl of the vector dot dA would be minus 2y dy dz, and we are supposed to integrate over this within appropriate range of y and z. So, what would be the range of y? The range of y, as we can see, will be from 0 to 2 minus z, that is from 0 to this line, this slanted line that we have, and the range of z would be from 0 to 2. So, for performing this integral, we will have to first perform an integral over y. So, the argument will be minus 2y dy, and the limit of this integral will be from 0 to 2 minus z. And then whatever we get after performing this integral, we perform the z integral on this over the range 0 to 2, and by performing these two integrals we will obtain the value minus 8 over 3. Please perform this integral yourself. And we have to see the same thing using the line integral as well. So, how do we do that? We consider the lines that are shown here using the arrows, take the line elements accordingly. So, the line element along z axis in the direction given is minus dz z cap, along y axis it would be dy y cap, and along the slanted line we have to find this out. It will that line element we can find out by differentiating the equation of the line. We have dy equals minus dz there, and from that we can find this line element, and putting appropriate limits we can perform the line integral. Please perform the line integral yourself and try to verify whether Stokes theorem is valid for this system or not. Obviously, the answer would be that the Stokes theorem is valid. It is in general valid for any kind of situation. So, here it should also be valid. Please verify that yourself. Now, let us consider the second problem of this tutorial. The second problem wants us to verify the divergence theorem in spherical coordinate. So, we are given a vector field V given as r cosine theta along the direction r cap, that is the r component of the vector. The theta component is r sine theta, that is along the direction theta cap, plus the phi component is r sine theta cosine phi, that is along the direction phi cap. This is the vector field that we have, and we are supposed to verify the divergence theorem. And the divergence of a vector field V in spherical coordinate system, this is the expression for that. We have obtained this earlier, we have written this down earlier. It is 1 over r squared del r squared, the r component of the vector, plus 1 over r sine theta del theta sine theta times the theta component of the vector, plus 1 over r sine theta del phi of the phi component of the vector. Now, this problem asks you to check the divergence theorem for this the given vector field here, and you have a inverted hemispherical bowl of radius capital R resting on xy plane and centered at the origin, like the picture here. So, you can consider it as a northern hemisphere, only that thing we have. So, the surface here is a curved surface and a flat surface for the surface integral part of the divergence theorem, and the volume is that of a hemisphere, only the northern hemisphere in this case. So, how do we obtain northern hemisphere in terms of spherical coordinate? We can have r, small r going from 0 to capital R, that gives us the range of r. Theta will range from 0 to pi by 2. If we go to pi, that will give us the entire sphere. For the northern hemisphere, we will have it from 0 to pi by 2. For southern hemisphere, it will be pi by 2 to pi. So, this is the northern hemisphere, we will have from 0 to pi by 2, and phi will span the entire region, that is 0 to 2 pi. Okay, now you can pause the video and verify the theorem try to verify the theorem yourself, the divergence theorem. After doing that, you can replay the video and see how we can actually do it. Okay, so if we calculate the divergence of the given vector, the expression would be 1 over r squared del r of r cubed cosine of theta, plus 1 over r sine theta del theta of r sine square theta, plus 1 over r sine theta del phi of r sine theta cos phi. So, the divergence of the vector turns out to be 5 cosine theta minus sine phi. And if we perform a volume integral over this divergence, So, we will have to multiply it with the volume element, and the volume element in this context is r square sin theta dr d theta d phi. We have already talked about the ranges of r theta and phi. So, if we put the appropriate ranges, r integral over r, the range is from 0 to capital R, integral over theta, the range is from 0 to pi by 2, the integral over phi, the range is from 0 to 2 pi, the integrand is 5 cosine theta minus sin phi multiplied by the volume element r squared sin theta dr d theta d phi. If we perform this integral, please perform this integral yourself, you will find 5 pi capital R cubed over 3. So, this is the volume integral of the divergence. Now, we have to perform the surface integral v dot dA over the surface that encloses this volume. So, which surface encloses this volume according to this picture? The curved surface of the spherical curved surface plus the flat surface that is lying on the xy plane here. So, we will have to consider both surfaces. How do we do that? Over the hemispherical surface, we can take the surface element dA vector that is given as that is along r cap direction perpendicular to the surface, and the magnitude of that element is r squared sin theta d theta d phi. That is something we are already familiar with. So, over that hemispherical surface, curved surface, the surface integral v dot dA becomes the range of phi is from 0 to 2 pi, range of theta is from 0 to pi by 2. We have v dot r cap capital R squared sin theta d theta d phi. So, we will only have the r component of the vector relevant here, everything else will go to 0 because we are taking a dot product along with the r cap direction. So, we will have integration over capital R cosine theta, capital R because at this surface, on this surface the value of small r will become capital R, times r square sin theta d theta d phi, and if you perform this integral you will find pi times capital R cubed as the value of this integral, and we are left with the flat surface now. On the flat surface, dA will be along theta cap direction. Theta cap direction means perpendicularly below, minus z direction on that xy plane. Theta cap direction changes its direction depending on what value of theta you are considering. For theta equals pi by 2, the direction is minus z direction, and that is the direction of this surface. We always consider outward direction as the direction of the surface. So, it is theta cap r sin theta d phi dr, that is the surface element. Now, remember that r is a variable in this case, small r is a variable that has range from 0 to capital R, theta is fixed, that is pi by 2, and phi has a range from 0 to 2 pi. So, we will perform this integral for over this surface, theta is pi by 2. So, we have a fixed value of sin theta, that is sin pi by 2. So, the second integral over the flat surface v dot dA becomes integration over phi from 0 to pi by 2, integration over r from 0 to capital R, v dot theta cap r sin pi by 2 dr d phi. So, only the theta component of the vector will be relevant here, and that will after performing this integral you will find this equals twice pi r cubed over 3. Now, if you add the first and the second integral, you will find the total is 5 pi r cubed over 3, and that is what we found from the divergence by performing the volume integral over the divergence. So, the divergence theorem is verified for the given vector in spherical coordinate system. Now, let us consider a third problem in this tutorial. You are given a vector v in spherical coordinate system. It is given as r cos squared theta along r cap direction minus r cos theta sin theta along theta cap direction plus 3r along phi cap direction. Now you are asked to compute the line integral of this vector along the path shown in the figure. So in this figure we have a triangular part in the YZ plane and a quadrant of a circle in the xy plane. This is the path, the direction is given here. You are supposed to use spherical coordinate system, although the path is shown in Cartesian coordinate system, and the coordinates that are given for different points in this diagram are also in Cartesian coordinate system. Because the vector field is given in spherical coordinate system, it will be much easier to convert these coordinates given in Cartesian coordinate system into spherical coordinate system and perform the line integral over the shown direction. And then check your answer against Stokes theorem. What does Stokes theorem tell us? Stokes theorem tells us that this line integral that encloses a surface, a part of the surface is lying on xy plane and another part is lying on yz plane. So this surface is enclosed by this line that is shown here, and the line integral of the vector along this line that is shown here would be equal to the surface integral on the shaded surface of the curl of this vector. That is something we are supposed to verify. Now please pause the video and try doing it yourself, and then restart the video later. Okay, so if we want to perform the line integral, we can start at the origin, and the first thing we note is that r on the first line segment is ranges from 0 to 1, theta is fixed, that is pi by 2, and phi is 0. So dl, the line element, is r cap dr. On the second, that is the arc that we have on xy plane, there r is fixed, that is 1, theta is pi by 2, that is also fixed, and phi ranges from 0 to pi by 2 there. So dl, the line element, is phi cap r sin theta d phi. And then on yz plane, the third line segment that is along the z direction, we can have theta fixed at pi by 2, and r sin theta will be y, that is 1. So r will be 1 over sin theta, and dr, that is something interesting, it will be minus 1 over sin square theta cos theta d theta. Please find out how it becomes that. This is if we have r given as 1 over sin theta, then this would be the expression for dr. Theta would be pi by 2 to theta naught, that would be the range of theta. Theta naught is the value of theta at the top of that line. So theta naught will be given as tan inverse of 1 over 2, and dl, the line element along this line, the vertically upwards line, that is a line along z direction, would be given as r cap dr plus theta cap r d theta. And finally, along the fourth line, that is the slanted line coming back to the origin, along that line theta equals theta naught, the fixed value of theta that we have obtained earlier, that is tan inverse of 1 over 2, phi equals fixed pi by 2 here, and r, that ranges from 1 over sin theta naught to 0. And well, we have to find the dl, the line element, that is along r cap direction, and dr. R cap dr is the line element along this slanted line. So please perform this line integral, and then we are supposed to perform the surface integral of the curl of this vector v. So please calculate the curl of this vector. After evaluating the curl of the vector v in spherical coordinate system, we need to perform this integral over two surfaces. One surface is on yz plane, so dA would be minus phi cap, that is above the screen, that's the direction above the screen, times r dr d phi, and the other surface is on xy plane, and here the direction is along z axis. So, it is minus theta cap for xy plane points along z axis times r sin theta dr d phi. These are the two surfaces where we are supposed to perform the integral, surface integral of the curl of the vector. And please perform these integrals and verify the Stokes theorem yourself. That is the end of tutorial 2.